The Linux kernel is falling apart. There have been a tranche of bugs that have come out, one of them so complex that even Mythos missed it. Now, you know the video is serious and getting pretty bad when I'm referencing LinkedIn, but this guy makes a really good point. So it was 1 every 5 to 10 years, and now we have 2 in a week. What he's talking about are these things that are known as universal LPEs, universal local privilege escalations that are able to take a non-privileged user on a Linux box, a very common server scenario, and that user, by exploiting this vulnerability, can become root and completely compromise the device. It used to be 5 to 10 years. What he means here are bugs like Dirty Cow. If you were in the industry in 2016, man, when Dirty Cow dropped, that was such a big deal. The way that the copy on write system worked, there was a vulnerability where you were able to erase a copy on write and use that to rewrite files in the system, and you could turn a file like sudo into your own program, giving you control of the box. A bug like this was a really, really big deal because every version of Linux was vulnerable to it, and it was fairly simple to exploit. When it came out, there was a POC, and you could just run it and become root. You know, the kernel community scrambled to patch this bug, rightfully so, and it became kind of the hallmark of like the perfect LPE. And a bug like this really didn't exist for like 8 more years, where Dirty Pipe came out. This one's the same idea. It was a universal LPE in the way that pipes were handled in the kernel, allowing an arbitrary user to overwrite data in an arbitrary read-only file, making them able to overwrite the contents of executables and run their own code as root. So we've had kind of this pattern where it took a very long time for these bugs to pop out, and now what he references in this post again 2 months ago is we have 2 in a week. He's referring to copy fail and dirty frag. And since then, there have been other bugs. Again, the ePoll one we'll go into here in a minute. This kind of highlights an interesting pattern where we're seeing these researchers use AI to discover new patterns of vulnerability, right? All VR is, vulnerability research at the end of the day, is pattern recognition, right? Is this system used in the way it's intended to? Do they misuse this function? Is that function exploitable or reachable? If the answer is yes, you're going to have a bad time, right? One of the hardest parts about this industry is figuring out what CVEs apply to me, which ones actually matter that I have to fix. And that's why today's video is sponsored by Maze. Maze has spent the last couple of years finding and mitigating vulnerabilities in cloud deployments, and they've moved on to source code through the new tool Maze Code. And I think it's really awesome. So here is your worst nightmare if you're maintaining a code base: 99,000 vulnerabilities that you don't really know if they're real or not. And the way they solve this problem is really, really cool. So in this example, you have urllib3 decompression bomb. This is a CVE where basically URL3 could be urllib3 could be DOS because of the way that it decompresses HTTP3 packets. What Maze does is really cool. They look at not only if your code uses urllib3, but is the vulnerable part of the code base reachable? Does it matter in your deployment? What they do is they can look at your infrastructure in AWS and also the images on AWS and tell you based on how that image is deployed and its internal settings if that actually matters. So for example here, yes, the code base in question does use urllib3. Oh, but the way it's deployed and the way the network is set up means that you cannot access this code base. So it's reachable by default, but because of the way that the outbound URL is set, it's fixed, meaning that you can't actually hit this bug. And by this process of elimination, what we do is we take 100,000 vulnerabilities and reduce them to less than 1%, only 786 of which are actually critical. That being said, that's a lot of bugs, but it's a lot less than 100,000. If you guys want to learn more, check out this link here. Go check out, learn more about Maze and how you can reduce the overall security debt in your code base. Thank you for sponsoring the video, Maze. Let's get back to it. Copy.fail kind of set the tone for the new landscape of kernel exploits because it kind of showed if you can find a single pattern in the kernel where something has gone wrong, it may exist in multiple locations in the kernel. The way that copy.fail works is effectively you take 2 file descriptors, right? A file that you do own, like a socket, and then a file that you don't own, like bin su, for example, and you splice them together. The splice operation is a syscall, and the reason I use syscalls is when you're doing kernel exploitation, the only real levers you have to play with are either drivers that have vulnerabilities in them or syscalls. All of those are just code in the kernel that can potentially be implemented incorrectly. Now, what happens in copy.fail is super interesting, right? Because of the way that the kernel implements its crypto subsystem for one of the socket types, there is a vulnerability where temporarily in the kernel, 4 bytes get written outside of the page cache entry of one of the file descriptors, right? You have your socket that you do own and your other file that you don't own, and you're able to use that to arbitrarily in memory overwrite the page cache of another file with your own data, giving the kernel the perception that the data is whatever you told it was. So you can run bin-su and it will then run your code. Again, I have a whole separate video on copy-fail. I'll put it here in the cards. But this kind of broke everyone's minds. Like, wait, okay, if this bug exists in Splice here, what other subsystems in the kernel do this out of bounds write on page cache entries? And then literally like 2 weeks later, Dirty Frag came out, which again, another Linux LPE that's universal. Again, the dirty part kind of mimicking Dirty Cow here. And it shows that, okay, this one bug came out by one researcher, and then someone found a bug very similar that also uses that splice primitive to find vulnerabilities where there are out of bounds page cache writes in ESP. Kind of funny, he even comments on the dirty thing in the README. Another branded dirty series? Yeah, I know. However, this is a descendant of Dirty Pipe, and it is a bug class that dirty is a frag. Like, he's commenting on it. It's very funny. But to my point about this pattern thing, right, he even says, what is the relationship with a copy fail vulnerability? Copy fail was the motivation for starting this research. In particular, the ESP cage cache write in Dirty Frag vulnerability shares the same sink as copy fail. It's the same kind of pattern that copy fail uses. Now, I've already made videos about those other LPEs because they're very interesting and they were hot like 2 months ago, and I wanted to kind of, break down how they work. But this new bug is interesting for a variety of reasons. One, it highlights a new pattern that we see new bugs coming out that exploit, use after freeze in kernel structures with a bit of like a confused deputy issue going on. Not like necessarily the same, but it's similar. And also what I love to highlight here is the bug that was missed by Mythos. And we'll go into why that is the case here in a minute. So bad epoll is another LPE that came out, I believe, 3 weeks ago. It's July 14th at this point, that takes advantage of a use after free in the kernel when you are using the epoll syscall. A lot of words there. Let's go into it. So epoll, by the way, is like the foundation of all async systems, right? If you use like an event loop, like libuv, for example, all of that is built on top of the plumbing that epoll provides. Epoll is a syscall that is an IO event notification facility. Basically what you do is you give it a list of file descriptors to that syscall, and it will block and return to you a list of file descriptors where IO is available. It's able to be written to, it has data for you to read from, etc. Okay. All async is basically built on top of epoll. And so inside the kernel, there are different ways for you as a user mode process to interact with epoll, which is exactly what I said before. All you have for kernel exploitation is like these user mode levers. Now, what makes this bug so crazy is it's so difficult to exploit, and the race window is so tight. This went unfound for a very long time. Again, this is a bug that Mythos missed, again, for 2 reasons we'll go into here in a minute. But the way the bug works is basically you have these things called epoll objects, and you can actually link them together, right? It's basically a way of conjoining like two sets of epoll data. And if you link two epoll objects, closing both of them at one time triggers a race where while one is closed, the other is temporarily writing data outside of the bounds. The other one is using the epoll structure that has been freed to do a write. And again, you can read the write up here. I'll link it in the description below. It's a lot more complicated than I'm making it out to be. And I don't want to try to describe this graph to everybody on Earth. I think I still personally don't get it like super well. But the primitive here is a use after free when you link two epoll structures together, which is super interesting. What you're able to do with the use after free is typically have some kind of object type confusion, not objects in C, but like a type confusion of a structure where you put another structure in place of that data and change the data there so that when the use after free occurs, you can turn that into like an 8-byte write, for example. So the exploit eventually turns this 8-byte write into a use after free on a file object, and then you use a cross cache style attack to basically mimic the actual contents of the data, sort of like the page cache thing that the other exploits did. Super interesting. But I want to highlight here, why did Mythos miss this? How is it possible that Mythos, the end-all be-all of cybersecurity research, didn't find this bug? Now, Mythos missed this for 2 reasons, supposedly. One, again, this is a race condition that occurs in a 6 instruction window. So if you're not really like aware of what's going on in the code base, it's very hard to look at that and like discern that there is a race, right? Again, the issue with use after free vulnerabilities is they are not necessarily like spatial in their execution, they're temporal. So you have to like be able to mentally see 2 states of the program at once. And it's very difficult to understand like both like mathematically from like a computation standpoint, but also like human discerning. But also the even cooler part, and I searched ASAN to show you guys, and the first result you get when you search ASAN is autistic self-advocacy network, which We'll talk about Clang. So Clang has this tool called ASAN Address Sanitizer, which basically is a way to instrument your code so that as you're running your code doing testing, if you do an integer overflow, an integer underflow, a buffer overflow, a use after free, there is a runtime that is checking all of these accesses to make sure that you don't do this, right? The issue is the kernel ASAN that was compiled into the kernel that is doing these checks. I think Mythos and all these models depend on using all of these toolings. A lot of these models depend on tooling that already exists, like ASAN, for example, to find the bugs that easily kind of just fall out like that. The window for this use after free is so tight that literally the checks that ASAN runs to detect use after freeze does not run in this window. So like the free happens here, the write happens here, and then after that is when the use the ASAN like reference checker is running, right? So like there's not even a window large enough for ASAN to detect it, which is another reason that Mythos did not catch this vulnerability. And literally as I was making this video, someone sent me this write-up for a different bug I'm not going to go into because I don't understand it yet. I tried to get it ready for this video and it is so complex. It literally comes off like the turbo encabulator meme video on YouTube. Go read this article yourself. I'll make a video on it here in a couple weeks when I fully understand it. Now, bad ePOL was found by Jay Jiang. I'm going to mispronounce your name. Jiang Chung. I'm so sorry if I mispronounced that. He found this by hand, like with his eyes, because it's such a difficult window for not only ASAN but AI to discover. But the point of this video is kind of to highlight, I think it's only going to get worse from here, and not in like a doomy gloomy kind of way. I think this actually is a good thing net for the community where we have these bugs that are getting found out, right? The highlight that this guy makes is what changed our tools. We are witnessing the great backlog clearing. These vulnerabilities aren't new. They sat dormant in open source code for a long time. The only thing protecting them was a lack of human bandwidth. I totally agree with this. These bugs are so complex. Any kind of vuln research gets siloed by the knowledge of the researcher, right? You have your kernel exploiters, you have your hypervisor exploiters, you have your embedded guys. Now, because of AI-enabled research, anybody can kind of do this research by figuring out what patterns are popular and going and finding new uses of those patterns in the kernel that could be incorrect. So if you're like a defender, if you're trying to figure out what do I do about this, honestly, I don't know. No, I'm kidding. The answer is just stay on top of patches, right? Make sure you're very aware of what bugs are out. Watch my channel and figure out what bugs matter for you guys. My newsletter also, I sent a newsletter out that talks about what bugs are trending and hot right now for the exploiters in the world. Yeah, man, it's an interesting world for sure. I think what's going to happen is code will get much more safe to a point where it's almost like beautiful, and we won't talk about this much anymore, on the order of like 5 to 10 years. But within that 5 to 10 year window, it's gonna be a bumpy ride, the Harry Potter Azkaban DVD menu. All right, guys, thanks for watching. I appreciate it. Bye. You thought I forgot. You thought I forgot the main point of this video. Would Rust have fixed this? The Lord's Rust? So like technically, yes, from a pure like language semantic standpoint, right? Like Rust has the whole ownership system where it does like at compile time reference counting and ownership, where you're not able to do this thing where you have a use after free. It's like the whole point of the language. That being said, it's very difficult to write Rust in the kernel because of the way that Rust operates. So like, yes, if the Linux kernel were written in Rust, this would not be a thing, but also writing it in Rust is much harder. So like 4 out of 10. I don't know why I did the Mr. Miyagi thing, but anyway,